Hi, I'm Shanawaz. In last lecture we were discussing homotopy equivalence and we did some examples on contractible spaces and homotopically equivalent spaces. Now let us begin this lecture with the following example. Let us consider a topological space X which contain all elements of R2 such that 1 over 2 is less or equal to norm of X is less or equal to 3 over 2, and let A be a subspace of X and let A be the set of all elements of R2 such that norm of X is 1. Now this is clearly a subset of X. Then we have to prove X is equivalent to A. I mean homotopically equivalent to A. Then X is equivalent to A. Now to prove this X is homotopically equivalent to A, it is enough to prove that there exists a continuous deformation retractor of X onto A. Now this topological space is actually an annular region. Now it contains all, suppose we consider a circle of radius half and a circle of radius 3/2. Now let us make it a little bigger. So this is our annular region, this is our X, and this is this set A. It contains all the pointers of R2 which lie on the circle of radius 1. So this is over A. Now what we have to prove? We have to prove X is homotopically equivalent to A. So in order to prove that, we first define a retractor of X onto A. Define a map say define a map R from X to X by R of X is equal to the X over norm of X. So obviously this is well defined map because X cannot be equal to 0 since X belongs to X, and this capital X is this annular region and it does not contain 0. So this is a well defined map. Now if we look, now clearly this Rx, this is again a point of X. Now if we take its norm, that becomes 1. So one can note that this Rx is in A. So one can note that this R of X is a subset of A, and if we restrict R to all the pointers in A, then it behaves as an identity function on A. So this is the retract of X onto A. Now to prove that X is homotopic to A, to prove that X is homotopic equivalent to A, we need to prove, so actually we have X here, this is A here, and this is the map, say R. Actually this R is from X to A, X to X, and from A to X we have the natural inclusion map. Now if we prove that R composite with I is homotopic to the identity on A, and I composite with R is homotopic to the identity on X, then we are done. In that case, X and A will be homotopically equivalent by definition. To prove X is homotopic to A, we need to prove, we shall prove that, we need to prove that R composite with I is homotopic to the identity map on A, and I composite with R is homotopic to the identity map on this space X. Now this is clear, since R composite with I, now R composite with I is a map from A to A. We have A, it goes to X, and X, from X to A we have this map R, sorry, we have this map we have this map R. So we have to prove, so I takes A into A and R takes A here, A to A identically. So this is actually equality here, this is actually the identity map on A, and hence R composite with I is homotopic to identity on it because of this equality. Now it remains to prove that it remains to prove that I composite with R is homotopic to the identity map on X. So to prove this, we have to exhibit a homotopy between these two maps. Define this is called the linear homotopy. Define H. One can note that here I from A to X is the inclusion map. So this is the inclusion map. define H from x cross 0 1 to x as h of xt, it gives is defined to be 1 minus t times identity on x plus t times this map I of Rx. So when we substitute, when we restrict h to 0, we get this id x of x, sorry, we get id, so this is actually equal to 1 minus t of x plus I of Rx. So I won't make any difference, so this will be t times R of x. Now R of x is given to be x over norm of x. So when we restrict h to 0, we get x, and that is same as identity on x. And similarly, when we restrict h on 1, we get x over norm of x, that is R of x, and which is same as I of R of x, because I is inclusion map, it won't make any difference. So this is I of R of x. So this proves that these two maps are homotopy. Now what this homotopy actually does, so we have this angular region here, and this is our circle. So when we put x here, it takes some point here x. So this is actually a line segment joining the point x and this point x over norm x. Now certainly this point x over norm x will lie somewhere on, so suppose this is point x here, so this point will lie on the circle here. So this is x over norm x. So what does this homotopy does? It takes this point to this point like this. Now if this point x is here, then again the point x over norm x will lie on a, which is this circle. So in that case it takes this point to this point. So what this homotopy does, it contracts the points on this line segment from here to here to this point, and points on this line segment from here to here in this direction. So all points in this angular region, they get as contract, they get all back down to this point. So finally when we do this for all points, these two spaces, I mean x and a, they are homotopically equivalent because one can be contracted to other. Hence this identity map x on x is homotopic to the map I of R of x. Therefore x will be homotopic to a. Let us do one more example. let us take the space Dn, where Dn is the n-dimensional disk, and we claim that this is another example. We claim that this disk Dn, this is homotopic to some point x naught, where this x naught is a point in D to the power n, where D to the power n contains all n tuples of Rn such that norm of x is less or equal to 1. So we have to prove that Dn is contractible to a point. Now we know that in order to prove some space is contractible to a point, we need to prove the identity map on the space, which in this case is Dn. We need to prove that this map is homotopic to a constant map. So if this is the case, then this Dn will be homotopic to Dn will be a contractible to point x naught. So to prove this, define R from Dn to this x naught. Clearly this is a constant map, because this entire space, this entire disk goes to this point, so this is a constant map. So R of x will be equal to x naught for all x in Dn. So it's a constant map. So what we need to prove, we have to prove Dn is homotopic, homotopic equivalent to x naught, i.e. Dn is contractible. It is enough to prove that the identity map on Dn, this is homotopic to the constant map. So we have to exhibit such a homotopy. Define. So again we are going to define a linear homotopy. Define H from Dn times the interval 0 1 to x naught. Or we can define to Dn. Let us define x naught by let us take D here. By h of xt as 1 minus t identity map on x of x plus t times this map R of x. So this is same as 1 minus t of x plus t of x naught. So that h of x0 is x, which is identity map on x, and h of x1 is x naught, which is the map R. So these two maps are homotopic. Therefore ID of x is homotopic to R, which is a constant map, which is equal to R. Therefore, hence our space Dn, this will be contractible to this point x0. Now notice here, this is, let us suppose consider two-dimensional disc D2. So this is our point, suppose this is our point x0 here. Now let us take a point x here. Now what this homotopy does, it joins this point x to x0, because this is a line segment through point x0 and x. So this is in this direction. So this point moves along this line segment to x0. Similarly, if we take x here, so it takes this x to this x0 along this direction. So all pointers are moving to this point x0 along all directions. So this space is gonna contract to this point. So this is the candidate for our homotopy. So this Dn will be homotopic to this point x0. Now let us do one more example. Let us consider two topological spaces x and y. Let x and y be two spaces. By two spaces I mean two topological spaces. Be two spaces such that y is convex. Now by convex set I mean a set is said to be convex if let us consider this set over here. So let us take this is one set and this is other set. Now this set is convex while this set is not, because a set is said to be convex if we take any two pointers in the set and join those two pointers. The line segment must wholly lie on the set, in the set. Now if we take a point here and a point here, and if we join these two pointers by this line segment does not fall entirely in this set. So this is not a convex set. So this y is given to be a convex space. So and f and g be two continuous maps from x to y. Then f and g are always homotopic. They are always homotopic. So why this is true? So if this is space x, this is space y. Now let us fix a point here. Say this is point x. Suppose that this x is mapped to point x0, x1 via, suppose via f, and the same x is mapped to x2 via the map g. Now because y is convex, we can always join these 2 points x1 and x2 such that this line segment lies wholly in this space Y. Now this is the main reason. Using this hypothesis, we can exhibit a homotopy. This is our map G. So the solution for this is we can define a linear homotopy. Define now if we consider the equation for this line segment which join is point x1 with x2, so the equation for this is 1 minus t of x1 plus t times x2. This is called convex combination because sum of these two coefficients is 1. So if we define, so this is same as 1 minus t times f of x plus t times g of x, because f takes point x to x1 and x to x2. So this will be our homotopy. So if we define our homotopy as from x cross 0 1 to y like this, so this will be a good candidate for the homotopy. So hence if we restrict this h to 0, we get f, and we get f, and when we restrict this h to 1, we get g. So f and g will be homotopic. Now let us define paths and path homotopy. Paths and path homotopy. So by a path in our topological space X, we mean a continuous map. Suppose we have a topological space X, then by a path in X we mean a continuous map from interval 0 1 to X. So if this is over X, then this is a path, a continuous map. So this is point f of 0 and this is point f of 1. So this path travels along this direction. So this f of 0 is same as, let us keep it x0, and let us keep this x1. So this is a path from x0 to x1. So we have the definition. A path in a topological space is a continuous map is a continuous map say f from this unit interval 0 1 to this space X. The point, this f of 0 is called initial point. And f of 1 is called the final point. Together these 2 points are called the end points. Now we can define multiple paths, and we have different operations on paths. For example, we can define the inverse path. So if we have a continuous path, suppose f is a path in X where X is some topological space. Let us suppose it's a path from x0, which is called f of 0, to x1, which is equal to f of 1. Then by inverse path, then the inverse path, which we denote by f bar, then the inverse path f bar of f is the new path in the same space X, that is f bar is from the unit interval 0 1 to X, such that which is given as f bar of S is, let us keep this argument X here, this f bar of X is f of 1 minus S. Now suppose this path f is from x0, which is equal to f of 0, to f of 1, which is equal to x1. So this is traveling along this direction from x0 to x1. Now what x does at 0, what f does at 0, f bar does it at 1, because when we substitute 0 here, this is x here. So f bar of 0 is f of 1 and f bar of 1 is f of 0. So this new path will be the same path but in the opposite direction. So this is f bar, this is f. So in the next lecture we'll define the product of paths.